This is Mesut Şahin speaking, and we'll talk about higher order derivatives. So, if the first derivative of a function y equals fx is differentiable at x itself, then we can calculate its derivative and call it the second derivative of f. So, derivative of the first derivative will be called the second derivative of f, and we'll use y double prime to denote it, or f double prime x to represent the second derivative. And there are various ways to denote the second derivative. Either we use y double prime, f double prime, or d square y divided by dx square, or in the language of operators, we apply this operator once and then we apply twice. So as a result, we can use d square divided by dx square in short to denote this operation. So this is also a notation. Or instead of this, we can use capital D square x sub x of y, or d square sub x of fx. So all can be used, and we've mostly used y double prime or f double prime or this notation. These are more common. And similarly, we can talk about the third derivative as being the derivative of the second derivative, and so on. And since usage of these double prime, triple prime will be difficult when the order of the derivative increases, instead we use y to the power n in parentheses in order to distinguish it from nth power of y. So higher derivatives will be denoted by this notation when n is big enough, or this one. And for the rest, it doesn't create a problem to use nth power, because there is no possibility of confusing with anything else. So d to the power ny divided by dx to the power n, or these notations will be used throughout. Okay, let's come back to the velocity, which is the derivative of a function f. So we have a moving object, and its velocity, as I told you before, is the instantaneous rate of change of the position of this object with respect to time. So if the object moves along the x-axis and is at the position x equals ft at time t, then the velocity will be the derivative of ft with respect to t. So similarly, the acceleration of the object is the rate of change in the velocity. So it's the first derivative of the velocity. Thus, acceleration is the second derivative of the position function. So the first derivative of the velocity will be the second derivative of the function f. So second derivative is also used in life as being the acceleration of a moving object. Okay, let's look at higher derivatives of the function fx equals x to the power n, where n is a positive integer. Then, if you think about it, you'll come up with this formula for k between 0 and n. So, k's derivative of the function f will be given by n times n minus 1, n times 2, blah blah, n minus k minus 1 times x to the power n minus k. And after nth derivative, you'll get a constant function, and derivatives you compute will be 0. So that's why after k bigger than n, you'll get 0 to be your derivative. So there is a notation here, n factorial and n minus k factorial, to denote this product in short. So let me talk about it. 0 factorial is conventionally 1, and 1 factorial is 0 factorial times 1, which is 1 times 1, so 1. 2 factorial is 2 times 1 factorial, so it is 2. 3 factorial is 3 times 2 factorial, which is 6. And n factorial is n minus 1 factorial times n. So the product of numbers from 1 to n is just n factorial. So if you think about it using this property, n factorial divided by n minus k factorial will be just n times n minus 1 times n minus k minus 1. So if you say the first n minus k product is n minus k factorial, the rest will be what is written here. So, but how do you prove that this formula is valid for all k? So, intuitively it is clear, because each time you apply the general power rule. Derivative of x to the power n is n times x to the power n minus 1, and derivative of this one will be n times n minus 1 times x to the power n minus 1 minus 1. So if you keep doing this, you'll get a formula like this for each k. But how do you prove this? So there is this induction method, which is very powerful for proving claims or formulas involving integers. So since k is an integer, we can prove this formula using induction. Let me illustrate this. So the base statement, the base case is for k equals 0. And in this case, the formula f0 here means n factorial divided by n minus 0, which is also n factorial. So this gives us 1, n factorial divided by n factorial, times x to the power n minus 0, which is x to the power n. So this formula gives us x to the power n when k is 0. And we know that this is fx. So the 0th derivative of f is given by this formula. So the formula is true for k equals 0. Now we assume that the formula is true for any k between 0 and n. And we check the formula for the next case, k plus 1. So assume that this formula is true for k, and we take derivative of this. So k plus first derivative is the derivative of the kth derivative, and we assume that the kth derivative is given by this formula, so we take derivative of this. So derivative of this is the constant here times n minus k times x to the power n minus k minus 1. So the constant here times the power n minus k times x to the power n minus k minus 1. So if you rearrange this, n minus cancel and n minus k will cancel here, so that you have n minus k minus 1 factorial here. So n factorial divided by this n minus k minus 1, or n minus in parentheses k plus 1 factorial, times x to the power n minus, this part is written as k plus 1 inside parentheses. So, and this is the formula here for k plus 1. So we check that this formula is true for the k plus first derivative. And this completes the proof. Whenever the formula is true for k, it's going to be true for k plus 1. So we know that it is true for 0, and this mechanism makes sure that it's going to be true for the first derivative. And when the first derivative is obtained via this formula, this mechanism makes sure that the second derivative will obey this rule as well, so on, so forth. So this proves that the formula is true for any k between 0 and n, including 0 and n. But when k equals n, this is 0, so x to the power 0 is 1, and this is n, so this is 0, 0 factorial is 1, so this nth derivative will be just n factorial, so which is a constant. So nth derivative is a constant, so higher derivatives after n, so n plus first derivative will be 0, n plus second derivative will be 0, and so on. So all the derivatives after n will be 0, so we have this part. So this proves the claim completely. Let's look at the second example in this regard. So we are given a function y in terms of constants a, b, and k. So a, b, and k are constants, and y is given by a times cosine kt plus b times sine kt. And let's verify that this function is a solution of the second order differential equation given by the formula here. So let's verify this equation is satisfied for this y. For this, we need to compute second derivative of y, and before doing this, we need to compute the first derivative. So the first derivative of this sum is the derivative of this part plus derivative of this part, and if you use all the rules you have seen until now, it is easy to get that derivative of this part is a times derivative of cosine times derivative of kt. So derivative of kt is k, so k times a will be here, and derivative of cosine is minus sine, so you have this part. Similarly for b times sine part, so derivative of what is inside of sine is k with respect to t, so you have k here. You have a constant b here, and derivative of sine is cosine. If you apply taking derivative operation, differentiation with respect to t again, you get from here that derivative of kt will be k, so you get k square, and then derivative of sine will be cosine, and you have a here. So ka becomes k square a, and sine becomes cosine when you differentiate with respect to t. Similarly, this part becomes k square b because of derivative of kt. So k square b comes from here, times derivative of cosine, which is minus sine. And if you think about it, so you have k square in common, so in minus k square parentheses you have a times cosine plus b times sine, which was the original function. So this is exactly what minus k square y is. Hence, second derivative plus k square y is 0. So that the differential equation here is satisfied. So this is an illustration of the second derivative. Okay, our final example involves derivatives of reciprocal of 1 plus x, and here is how to find formulas. So the first derivative is clearly minus 1 times 1 plus x to the power minus 1, which is minus 2. Second derivative minus 2 times minus 1 times minus 3 as a power here of 1 plus x. And in the third derivative, we keep doing the same thing, applying the power rule for differentiation. So minus 1 times minus 2 will be multiplied by minus 3 here, and we decrease the power by 1, so we get this. So we keep doing this, but we need a formula which is valid for any integer bigger than or equal to 1. So intuitively it is clear that the formula should be this one. So the nth derivative will involve minus 1 to the power n times n factorial, because you have a product of 1, 2, 3, 4 and etc. 1, 2, 3 dot 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 n, which is n factorial. And so the power of 1 plus x will be minus n minus 1. So in the third power you have 4 here. So in the second power you have 3. So in n you'll have minus n plus 1. So this is true for all n that is bigger or equal to 1. So the base case for the induction is n equals 1, and which is verified here at this step. So when n equals 1, you have this part equal to this part, and when n is 1, this is minus 1 to the power 1, which is minus 1. 1 factorial is 1, and if you insert 1 here, you get minus 2. So from here, it is clear that this formula is true for n equals 1. Now assume that the formula is true for n equals k, so that we have this formula. Now we compute k plus first derivative by taking derivative of this one. We are assuming that this formula is true. I can take derivative of both sides. Derivative of this is this one, and derivative of this part is minus 1 to the power k times k factorial. This part is constant. It is written here. And derivative of this part is minus k minus 1 times 1 plus x to the power minus 1 minus k minus 1 minus 1, which is minus k minus 2. So if you rearrange this formula, you get another minus sign here coming from here. So minus 1 to the power k plus 1. K factorial times k plus 1 will be k plus 1 factorial. And this can be written this way. So this verifies that the formula is true for n equals k plus 1, completing the proof. And thank you very much for your attention.